chapter 2 of the notes. So state space response. A little background. So in the mechatronics course, we learned how to represent systems mathematically in a way that's analogous to that input-output differential equation, okay? Instead of being a single input-output differential equation, we represent the system as a system of first-order differential equations and another equation that describes an algebraic relationship between the inputs, or among the inputs, states, and the output. So that's what's called state space, and there's a whole chapter in the Volume 1 notes called State Space Models, okay? Now, if you didn't go through that course and you're feeling a little bit scared about this, I will say that the focus is not at all in this course on deriving the state space model from the system description. Although we will spend a little bit of time doing that, specifically for fluid and thermal systems. And I think that reviewing the material from mechatronics course will help you immensely through that portion. But even if you don't feel totally comfortable constructing them, most of this course is not focused on constructing those state space models. It's what to do once you have that and trying to understand the system that you have. So this chapter is state space response, which is to say once you have that input-output differential equation or the state space model differential equation and output equation, what do you do with it? How do you construct a solution? And what does that solution mean? And how do we interpret things? So that's what this chapter is about. So let's do a little bit of review here in this sort of lecture 0 of chapter 2. Recall that for a state space model, the state x, input u, and output y vectors interact through two equations. So 2.1a and 2.1b are those two equations. Now, dx dt is the left-hand side of this first equation. So it's the time derivative of a vector, and actually, if we're going to be mathematically precise, it's the time derivative of a vector-valued function, right? So we often say that the state vector, or state x is the state vector, although it is really the state vector-valued function. So dx dt is the time derivative of each of these functions of time, x1, x2, x3, x4, in a vector, column vector. Now, that's not too bad. The right-hand side is a function of the state variables, so the state vector, u, the input vector, so inputs, just like in the input-output differential equation, are those quantities that are I guess, injecting energy from outside the system. And then time. So f is just some function. For each system, f is different. Okay? So it depends on how the system's connected, what the system consists of, and how you're modeling that system. The second equation, so the first equation then is just a matrix vector representation of a system of first order ordinary differential equations. Okay? So you may have experienced a little bit of exposure to that in your differential equations course. Sometimes they do cover that. Usually it's like one of the standard topics, but not every course gets to it. So systems of first order scalar differential equations are typically covered, and 2.1a is just that object. Now, 2.1b is the output equation, and really all it is an algebraic relationship, okay? So what you're saying is the output y is some algebraic function of the state vector, the input vector, and time. That depends on what you choose your outputs to be. So your outputs are arbitrary for a system, although when you're given a problem, typically I will say, like, these are your outputs. But they're part of the design decision that you need to make. What are the outputs? What are the variables in the system that I care about? Maybe it's a voltage across a capacitor. Maybe it's a current through a resistor. Maybe it's the velocity of some mass. Those are the output quantities that we might want to keep track of. Now, I will stop for just a moment and dwell a little bit more on what x is, the state vector, and what the input vector u is. And when I write them, I will draw the little arrow to denote that it's a vector. So the state vector x is a vector that contains variables that describe the system. So for instance, voltages, velocities, forces, etc. It's a very specific collection of them, though. It's a minimal set of such variables that describe the state of the entire system. Okay, so it's actually not unique. You can make different choices, but the actual number of state variables that represents the system is unique because it has to be a minimal set of variables. So we learned a very specific way to construct the state vector in the mechatronics course, but there are other ways to do it. We learned one way. U is the input vector, so that's going to have things like a voltage source, like a battery, something like that, connected to the circuit. That would be an external input to a circuit. Or perhaps a force on a mass would be some external force would be an input as well. So those variables would show up in the U vector. And so what we're saying is that the state variables change, right? So the time derivative of state variables. State variables change as a function of what the state is, what the inputs are, and what time it is. Okay? And that's the sort of the state space model concept, is that you've described how the system is going to evolve. State variables describe everything about the system, okay? And the inputs will contribute, and what the state is at a given time, contribute to how the state changes. Okay? And then the output is, once again, just what we are interested in. So the variables that we care about. We might care about one or more. So we might just care about one, in which case the vector y has one variable in it. But if we care about three, the vector y will have three variables in it. So that's the state space model. I did a little bit of in-depth in that, but I know there are a few of you who are unfamiliar with state space models, so I wanted to make sure we at least got a little bit of an intro here. And there's a lot more in the videos from from mechatronics covering that section, that one chapter. I think it's chapter 3 or something like that in the system dynamics. I set it on the Slack, so check it out. Okay, so the second equation, let's see. So in accordance with the definition of a state-determined system, given an initial condition, so that is the state at some initial time t naught, and input u, the state x is determined for all time greater than or equal to t0, to t naught. Determining the state response requires the solution, analytic or numerical, of the vector differential equation 2.1a. So this is the first one. So we have to solve that either analytically, so, with expressions, explicit functional expressions, or numerically, which is a sort of simulation. So we're actually going to learn how to do both of those in this chapter. We're just barely going to touch on the numerical side. Good. So the second equation, 2.1b, is algebraic. It expresses how the output y can be constructed from the state x and input u. This means we must first solve the state equation for x, then the output y is given by equation 2.1b. So we solve this equation, solve. It gives us x as a function of time. So it tells us what our state variables do for all of time, greater than or equal to 0. We take that and we plug it in to this equation, and that gives us y. The second part's pretty easy. The first part's the hard part, solving the differential equation. And that's actually not that bad, as we'll see. Okay. Just because we know that for a state-determined system, the solution to equation 2.1a can be determined, doesn't mean we know how to find it. In general, f is a function that is a vector-valued function. And g is also a vector-valued function. And they can be nonlinear functions. And actually, in the real world, a lot of things are actually nonlinear. We don't know how to solve most nonlinear state equations analytically. An additional complication can arise when, in addition to states and inputs, system parameters are themselves time-varying. Note the explicit t argument of f and g. So you see this explicit t in here. So sometimes the parameters themselves, like the mass or the resistance, vary with time, and that's when that t will come in explicitly. That'd be called a time-varying system. Fortunately, often a linear and also a time-invariant model is sufficient. And specifically, it's sufficient in some operating region, and I hope we'll have time in this term to talk about how to linearize a nonlinear system and represent it in a linear way. But suffice it to say that a linear model typically will work in some operating regime. So for instance, as long as the temperature stays close to this, it works just fine. Or as long as you don't flow too much current through this, it'll work just fine. So it works a lot of the time. Recall that a linear time-invariant system has state space model. So the left-hand side of each of these equations is the same. dx dt for the first one and y for the second one. It's what they equal that's a little bit different. So we said that this is for linear and time-invariant systems. So first of all, the fact that it's time-invariant means that these coefficient matrices, A, B, C, and D, are all constant matrices, okay? So those contain all the parameters of the system, like the mass and the resistance and the capacitance, etc. We say that for a time-invariant system, those parameters don't change with time. The variables like the voltage and the force, they will change, but the parameters don't change. The linear aspect is the fact that we are able to write this right-hand side of each equation as a product of a matrix and a vector, okay? So they're linear in the variables that are in x and linear in the variables that are in u. So they're linear in the states and linear in the inputs, okay? The reason why matrices are a big part of linear algebra is that they represent linear systems really well. We can't write a nonlinear system, like in general this is, in matrix form. But when we say it's linear, we can. We can write these as a matrix times the states a matrix times the input, another matrix times the state, and another matrix times the input. Okay. So this is the representation we're going to be spending a lot of time on. Okay. This representation has a lot of really nice properties that the nonlinear representation does not have. And it's a lot closer to our analytic grasp at the level that we're at. So we know how to do differential equation stuff, so ordinary differential equations, and that's what this is. We know how to do, most of us even before taking linear algebra could do matrix multiplication, matrix vector multiplication. That's all this really is, this equation. As we proceed in this chapter, we're going to get into eigenvalues and eigenvectors and some basis transformations and that type of thing, which are linear algebra topics. And, well, eigenvalue, eigenvectors are also in differential equations, so hopefully you saw them there too. We'll go over them again in this class just to make sure everybody's got it down. But next week we'll be covering that material. So hopefully the math doesn't trip you up. It's really not supposed to be mathematically beyond what you guys know how to do. And I think that it's roughly where most of you are. It's just within striking distance of where you guys are mathematically. So we'll explore this model extensively, and it's a super powerful model, as we'll see. So in this chapter, we learn to solve 2.2a for the state response. So like before, we'll solve this version, not the nonlinear one. We'll solve 2.2a. For the state response, x, and substitute the result into equation 2.2b, so the output equation, for the output response. First, we learn an analytic solution technique today, and then afterward, after some more analysis, we'll learn some simple software tools for numerical solution techniques. We're at least going to do a MATLAB one. I might also do a Python one, but at least we'll do MATLAB. And so you guys will get to see how to take essentially the A, B, C, and D matrices, pop them into MATLAB, and simulate the system almost effortlessly, like 2-3 lines of code. It's really nice. A little more than that in Python, but not too bad. Okay, good. So that's the intro